Hello, organic chemistry students. We're going to continue our discussion on chapter 2. And later, we're going to conclude the chapter with a discussion on a very important topic, which should be a review from your general chemistry, which is acids and bases. We're going to talk about the definition. How do we know the strength of an acid or a base, and how do we predict acid-base equilibria? But before that, let's continue our discussion with resonance structures. And precisely to tell you how you can distinguish, or how can you tell which structure is more stable than the other one. And for example, you might recall that in the case of nitrate, we have a resonance hybrid in which the negative charge is distributed amongst the three oxygen atoms in the same way. So it would be 1/3 of the charge. Nitrate has only one negative charge, so 1/3 would be distributed in each oxygen. It's evenly split onto the three atoms. In a similar way, acetate, which we can draw these two resonance structures in which one charge is localized in either oxygen, then the hybrid we can draw it as delta minus in each oxygen, in which the charge is split into the two. And so this we already know, but you also know that resonance structures are not always equivalent. And so how can we tell which structure is more dominant, or which one will contribute more to the hybrid of resonance? And there are a couple of factors, a few factors that we should consider. And the factors that I'm outlining here is in the order of importance. First, we need to look that for second row elements, we want a full octet, with the exception, this is very important to recognize that the carbons, like in a carbocation, may have an unfilled valence shell, that is 6 valence electrons. You already know that from your chapter 1, and so it's okay to have unfilled octet for carbon, but not for anything else, not for nitrogen, oxygen, or any of the halogens. We also are going to try to have the minimum number of formal charges and maximum number of bonds. So more bonds gives more stability. And of course, you want to place the negative charge on the most electronegative atom. For example, you want to have a negative charge on oxygens or nitrogens, but in addition, you want to minimize the charge separation, and you want the formal charges to be close together. You should recall that the resonance hybrid is the weighted average of all the contributors, and so that's why weighted average implies that we should know which contributor is the most stable, which one's the least stable, because that will be the major contributors and minor contributor respect. This is best illustrated if we show a couple of examples. In the case of the allyl anion, if you draw the resonance structure, you push this non-bonding electrons, the pi electrons go to this carbon in the corner. Now we have lone pair here, negative charge, and the newly formed double bond right here. You should know that based on this resonance hybrid, we're going to have delta minus in either end of the 3-carbon chain. And also, you should recognize that because of this resonance hybrid, this carbon right here, both of these carbons are sp2 hybridized, both of them. And so this is an exam question, or an exam-like question. If you see this as a carbanion, don't jump into conclusions and assume that this is going to be sp3 hybridized, because you have to consider resonance before you assign hybridization. Always, always, always. But in this case, we have a similar issue like the acetate anion, in which the charge is distributed amongst two equivalent atoms or structures. And so in this case, if you want to say which one's the major contributor, you would just circle both, or say, in this case, it's both. But how about when resonance structures are not equivalent? We have an example, this enamine, in which you take the lone pair, you form a new double bond right there. You kick this the pi electrons, and you place them right there in this carbon, and you have now a lone pair localized in this carbon with negative charge. That's a carbanion. And we have now a nitrogen with 4 bonds and a double bond, and now it's a positively charged nitrogen. Now let us examine it. So let's recall here, we're supposed to be looking for filled octets, minimum number of charges, maximum number of bonds. Let's see, we have filled octets in this one. Yes, we have minimum charges. That's right. And as far as bonds, we have 1 pi bond. In this other case, we have 1 pi bond, but we have 2 charges. So right here, we can see that this side is winning, because less charges and more pi bonds, or I mean, the same number of pi bonds, but at least less charges. Now, the third factor is negative charge in electronegative atom. So we don't have a negative charge except on this one. So I think we can stop our analysis here and conclude that this would be a good contributor, or one of the major contributor in this too. If we look at a similar example, this enol ether, you should also practice with arrow pushing. You kick in the lone pairs of oxygen, you displace the pi electrons into the carbon in the end. Now you have a carbanion with a negative charge, an oxygen double bond where there was no double bond is a newly formed double bond. Now it's positive charge, and a single lone pair in oxygen. In this case, we have again filled octets in both of them, and we have no charge. So this wins here, and this has charges here and the same number of bonds. So again, if we stop our analysis here, we can conclude that enol ether, this particular resonance structure, would be the major contributor. And you don't have to necessarily know in terms of what percent is this major or minor. You should just know and recognize this trend here. You're looking for field octets, minimum number of charges, maximize the number of bonds. You want to place negative charge on electronegative atoms, and you want the charges to be as close as possible. In the case of an enolate, let's just first draw the resonance structure here. We have non-bonding electrons are going to push out this pi electrons into the carbon in the end. Now the lone pair is localized there, negative charge. Oxygen now is a double bond, and instead of having 3 lone pairs, now we have 2 lone pairs. And we have only a negative charge. The charge was conserved. Negative in oxygen, negative in carbon. So it's -1 in both. And let us analyze. Fill octets for this side, yes. Fill octets for all of these sides is also correct. Minimum charges and maximum number of bonds. So here we have 1 charge, 1 negative charge, 1 negative charge, and 1 pi bond in both. So we have a draw right there. Now, negative charge on an electronegative atom. If you recall, oxygen is more electronegative than carbon. And so here we have the negative charge on carbon, whereas here we have the negative charge on oxygen. And so because of this, now we can conclude that, I'm sorry, it's the opposite. This is oxygen and this is carbon. We can conclude that this enolate is the major, as opposed to where you have the carbanion resonance structure. And so if you notice something here, I chose this examples because I want you to recognize the bonding pattern. We have a p orbital, or a pair of electrons that can be in carbon, for example, in the allyl anion, which was here. We can have a pair of electrons in a lone pair in the nitrogen, for example, in the case of the enamine here, or we can have it in oxygen in the case of both the enol ether and also the enolate. I want you to recognize, because this impacts hybridization. All of this species have sp2 hybridized carbon, nitrogen, and oxygen respectively. This is a very key aspect that all of you should learn to recognize. Okay, now continuing with chapter 2, we're going to move into a topic that you've already been introduced since your Gen Chem, and that is acid and base chemistry. And first, let's define what an acid and what a base is. And because we just moved from the topic of resonance, let's talk about the arrows that you should not use. You should not use resonance arrows when depicting an acid-base equilibria. And in that case, you should always use equilibrium arrows, which is one arrow going to the right towards the products, another arrow going to the left. In the case of acid-base chemistry, we have 2 main definitions, and let us focus on the first one. Historically, was the first one to be developed, and that is the Bronsted acid and Bronsted base definition. When it comes to Bronsted acid, you should always associate that definition with anything that can donate a proton, and a Bronsted base, anything that can accept a proton. So it's all about protons. When we're talking Bronsted, it's all about protons. Donation of protons and who accepts the protons. An acid will donate and a base will accept. And I want you to become familiar with a very generic or a general reaction scheme for an acid-base reaction. Of course, you should already know that an acid will be neutralized by a base, but what is the reaction that happens? The base will be the proton acceptor, and the acid will be the proton donor. So in general, this is a proton transfer reaction, proton transfer. From the acid to the base. The proton gets transferred from the acid into the base. And what gets formed? It's a conjugate base and a conjugate acid. And I want you to recognize this because it can be a little bit confusing. The acid, once it donates its proton to the base, it generates A minus, and because it has electrons that can go back to HA, this is what we call the conjugate base. The acid gives rise to the conjugate base, and the base gives rise to the conjugate acid. Why is this an acid? because now this can donate a proton. That's the reason why protonated bases are called conjugate acids. And this is important to recognize, because that will enable us to compare the acidity or the strength of both, and determine to which side will the equilibrium lie. So why is A minus a base? Because it can accept protons. And why is the conjugate acid, or Hb plus, an acid? Because it can donate protons. And so keep this in mind in this chapter and throughout our course. Now, if we look at a textbook example, the ionization of hydrochloric acid. This is a strong acid. This is a strong acid, and in water it will dissociate. And water, it's acting as a base, and it will accept the proton from hydrochloric acid. And what's going to form? This is now the base. This is now the acid. Now this is our conjugate acid, and chloride is our conjugate base. So if you recognize this general scheme that we just saw in the previous slide, then you will be able to then, upon establishing the reaction that you are looking at, and comparing the relative strengths. We're going to see in a minute how we do that. The relative strengths of conjugate acid or the acid. Which side is that reaction going to go forward or reverse? And the way we look at, and I want you to start to practice the arrow pushing. You should practice arrow pushing to show the transfer of that proton. The proton transfer reaction from the base, we have a lone pair, or it can be pi electrons. We will see in this case we have the hydroxide ion is going to pick up the proton from acetic acid, and the electrons that were making that sigma bond are now going into the oxygen, and we were going to have now a negative charge on the oxygen, and this is the acetate anion that you're already familiar, since we discussed its resonance structure. This would be the conjugate base, because this can accept a proton and go back to acetic acid. And water picked up a proton. I'm sorry, not water, but hydroxide ion picked up a proton and now became water. And now this is the conjugate acid. And notice the charge is conserved in this reaction. If we had a negative species like the hydroxide ion, we're going to end up with a negative species as well. In this case, the acetate anion. Now, if we look at this other example here, we have water and ammonia. In this case, in this particular example, I'm showing the arrows going, curved arrow going from the lone pair of nitrogen, picking up a proton in water, breaking the sigma bond, and the two electrons that were part of that sigma bond are now in the oxygen with a negative charge, the formal charge of -1. Nitrogen, on the other hand, now has a positive charge. It has 4 bonds. The charge was conserved as well. Charge was conserved. So overall is neutral. And in the left side, we have 2 neutral species. So the charge is conserved. Which one's the conjugate base? Upon deprotonation of water, hydroxide would be the conjugate base. Why is this conjugate base? Because this can accept a proton and go back. Why is this the conjugate acid? In this case, the ammonium ion. This ion, NH4 plus, it's called ammonium, and this is the conjugate acid. Why is this an acid? Because this can donate protons and go back to ammonia. Okay, now when we talk about strength of an acid, what exactly are we talking about? The strength of an acid, if you recall for any, if we draw the equilibrium of, in generic terms, I'm just putting HA, it's very similar to what happened with the ionization of HCl in water. If this is the solvent, in aqueous solvent, we have water picking up the proton from the acid, breaking the sigma bond, forming A minus with a lone pair. This is the conjugate base. And now this is the conjugate acid. Which side is the reaction going to be favored? Is it going to be favored towards the products, in other words, towards hydronium ion and the conjugate base, or towards the original acid? And because water is the solvent, it's usually not included here. We have the equilibrium constant, which all of you should be familiar with since you're gen chemists, the ratio of the product over the reactants. And if we're talking about an acid-base reaction, the equilibrium constant is nothing other than the acidity constant, or what we call as Ka, which is the ratio of the products over the reactants. In this case, the solvent is not included. We ignore the solvent in the Ka expression. Now, if an acid is very strong, that means it's going to want to donate its proton fully or to a large extent, which in turn will lead to higher concentration of hydronium ion and the conjugate base. And that will lead to high number of products, a small number of reactants. This will lead to a large value for Ka, and that corresponds to strong acids. This corresponds large equilibrium constant, which is the same as large acidity constant, which means that it's fully dissociated or largely dissociated into protons, which are not free, they're not dancing around on their own, but they're bound to the solvent, in this case water, and that will be the hydronium ion is basically the same, and the concentration of the conjugate base, which is the expression of Ka. Now, if we have a logarithmic scale, if we develop a logarithmic scale, the negative log of the Ka, this is what we call a pKa. And because the Kas, the numbers are not very convenient, they're very large number, they have exponents like the power of 50 or the power of 60, and they vary all the way to negative exponents, then it's not as convenient. And so we develop a logarithmic scale to handle those numbers much easier. And if we take the negative logarithm of the acidity constant, then we generate a new number, which we call pKa, which stands as the potential of Ka. So the potential of any number, for example, the pH, would be the potential of the concentration of protons. But pKa is the potential of the acidity constant. And in any case, this is only a mathematical expression, which we will see how we can use or implement those. There's a lot of values of pKa's that have been already tabulated, and so you don't have to spend any brain power on memorizing anything. You don't have to memorize those values. You will be giving those values, but you should recognize the meaning and the implication of what is a small pKa or a large pKa. Small pKa is the same as a large Ka, and that corresponds to strong acid. And a higher value of pKa, high pKa, then it's a weak acid. And this will become very powerful for us to predict and even estimate without making any calculations with calculator or anything. Simply predict with a rough number, ballpark calculations, whether a reaction is going to go to the right or to the left. Again, just to recap, stronger acids will have large Ka and small pKa, whereas weaker acid will have high pKa values and low Ka values. Let us look at concrete examples. In the case of, I have a reaction here. I'm sorry. Okay, now let us look at concrete examples, and let us compare the pKa of three distinct species. In one case, I have methanol, and we're talking about the acidity of that OH bond, the acidity of the OH bond in acetic acid versus the acidity of the CH bond in acetylene. The pKa of methanol is 17, acetic acid 4.7, acetylene is 25. Which one's the strongest? The one with the lowest pKa value. In this particular case, it's acetic acid. Its name says it all. It's an acid. Whereas methanol and acetylene, they're not acids, but they can be acidic and can be deprotonated. Now, we want to deprotonate ammonia, for example. The pKa of that NH bond is very, very high, 35. This is the highest pKa, and therefore it's the weakest of this four structures here. Now, one thing to recognize, the pKa tables usually give the values in what it's called normal conditions. And normal conditions are 1 molar concentration at 25 degrees Celsius in an aqueous solution. Now, the trend, as I mentioned earlier, the trend using Ka values is reversed. So, in other words, the lowest Ka will be for ammonia, which corresponds to the highest pKa, and the highest Ka would be for acetic acid, which has the lowest pKa value, the stronger acid. Again, this is something you should always be very familiar with. Just have very general reaction, Ha dissociating into a proton and the conjugate base. The acidity constant is the ratio of the products over the ratio of the reactants. In other words, the ratio of the ionized species over the concentration of the not ionized species, products over reactants. Now, knowing this Ka, we can then estimate how much we will have ionized and how much we will have not ionized. And for that, we need to compare the acidity of the species involved. In this case, the original acid in question versus the conjugate acid that we're going to form. Again, in an acid-base reaction, this will be bound to the base, will it be H plus or the protonated base. Let's continue with some examples and exercises. If you are confronted with a question, you have to label acid, base, conjugate base, and show the arrow pushing mechanism for the particular reaction. First of all, if we're looking ammonia and water, we don't know which one is acting as the base or which one is acting as the acid until we inspect the products. We see that ammonia picked up a proton, and if ammonia picked up a proton, this should have been the base. And we see that water donated a proton to ammonia and formed the hydroxide, and so this should have been the acid. And in turn, hydroxide now became the conjugate base, and the ammonium ion became the conjugate acid. So this is the first step in analyzing acid-base chemistry, recognizing what can behave as an acid, what can behave as a base, what is the conjugate acid, what is the conjugate base. Once we do that, then we will be able to predict equilibrium. Now, I want you to compare and contrast the equation on top with this equation at the bottom. We have the same species, ammonia and water, but notice that now we have a completely different distribution of products. Now we have hydronium ion and the amido anion, NH2 minus. In this particular case, which one was the acid? It looks like ammonia donated a proton, and so now this, instead of being the base as above, now it's behaving as the acid. Water, on the other hand, because it picked a proton from ammonia, it's behaving as the base. And in turn, the hydronium ion is the conjugate acid, and the NH2 anion is the conjugate base. So again, this recognition of acid base, conjugate base is key in determining equilibrium and dissecting acid base chemistry. And you should practice arrow pushing mechanisms for proton transfer reactions. This is THF, common solvent, and if it's going to get protonated, always the curved arrow starts in the lone pair, in this case in oxygen, goes to the proton, and then the sigma bond is broken. The two electrons that were making that sigma bond are now going to end up in A minus, and I'm using HA as a generic form for a Bronsted acid. And you are encouraged to use HA in any proton transfer reaction in mechanisms for your arrow pushing mechanisms. HA is a generic way of depicting a proton transfer reaction. In this case, which one's the acid? Of course, HA is the acid. This is the conjugate base. Sorry, not conjugate base, but the base. The lone pairs in the oxygen picked up the proton. Now we have the conjugate acid. Now it's the protonated species. In the case of now we have this amide. This is an amide functional group. Before you proceed, if you were to take the arrow directly from the oxygen, it's actually better if you think about resonance before. And so you know that this lone pair nitrogen is conjugated with this pi bond. And so instead of directly attacking with the lone pairs on oxygen, it's better if you first conjugate or kick in this lone pair in nitrogen to form a pi bond here. And then the arrow, instead of coming from the lone pairs, now it comes from the pi bond. From the pi bond. And now you go and attack the proton, you cleave or you break that sigma bond, and you still generate A minus with the lone pair and the corresponding conjugate acid. In this particular case is now the oxygen has now the proton. This is the conjugate acid. Now another curved arrow example is from the pyridine. And I'm giving you the name of these molecules because I want you to become familiar with functional groups starting now. So this pyridine is a heterocycle. This nitrogen has a lone pair, which is basic. It's going to attack this proton, and it's going to kick or cleave that sigma bond to place this lone pair now on A minus. And now the nitrogen is bound to a proton, and it's called a pyridinium ion. And now because nitrogen has 4 bonds, it's positively charged. And this is the conjugate acid. Another base or another acid-base reaction, proton transfer reaction, this carbonyl species, this is an aldehyde. It's a double bond and an oxygen bound to a hydrogen. The lone pair in oxygen is going to go and grab the proton from the acid. The acid is going to cleave the sigma bond, generating A minus with the lone pair. And the oxygen that used to be neutral with 2 lone pairs, now that lone pair has been engaged in that bond, that oxygen-hydrogen bond, and oxygen has now a positive charge. This is, as you would expect, the conjugate acid. Okay, now we're going to see how can we determine the direction of the equilibrium. And a question here, can you determine the direction of an equilibrium for the reactions shown here? And the answer should be immediately obvious to you and should be no. Why? Because we don't know the nature of the acid in question, although we can tell the nature of the conjugate acid. And so in order for us to know the direction of the equilibrium, we need to know the pKa of the acid in question as well as the pKa of the conjugate acid that we are attempting to form. Let's take a look at some examples. I have here a reaction, and we're trying to determine, is this reaction going to go forward, in other words, to the right, or reverse, to the left? We have acetic acid reacting with hydroxide to give acetate plus water. First things first, we need to identify which one is the acid. Obviously, in this case, acetic acid is donating a proton, and it's going to end up as the carboxylate or acetate ion. And hydroxide is the base, is the same reaction we had seen before. It's now going to take a proton and be converted into water. This is the conjugate acid. And so now the values that we must compare are the pKa of the acid, how strong is acetic acid, and the pKa of the conjugate acid form, how strong is water. Because, as you may recall, the direction of the equilibrium is always going to favor the formation of weaker acids. In other words, stronger acids are going to form weaker acids. And in this particular case, as it so happens, the reaction goes to the right. It's favored the direction of the products as drawn, because by comparing the pKa, we have acetic acid has a pKa of 4.7, and water, which is the conjugate acid, 15.7, about 16. Lower pKa is a stronger acid than higher pKa. And so because we're forming a weaker conjugate acid, the equilibrium is going to go towards the products, and it's going to proceed as drawn. Always very key is weaker conjugate acids are going to be favored. So if you're able to identify which one's the acid, which one's the conjugate acid, look at the pKa values. Of course, you don't have to memorize. You can look at a table. And after you compare the pKa's, then you can immediately tell, yes, this reaction is going to be favored this way, or no, it's going to be favored the other way. In this particular case, yes, we're going to favor the formation of water and acetate. And you can also think of this way. We have an acid. It's a strong base, a strong acid reacting with a strong base, hydroxide, to generate a weak acid, water, and also a weak base. So hydroxide is a stronger base than acetate, and acetic acid is a stronger acid than water. You don't need to know or to memorize pKa values. However, you need to know how to interpret and what are the implications of the relative strength of acids. I think it will be easier if we look at more examples. In this case, acetic acid plus hydroxide gives water plus acetate. We know the reaction goes to the right. But how about this other reaction? Now we have acetic acid and water giving acetate and hydronium ion. First of all, we need to identify our acids and our conjugate acid. Which of the two species here, either water or acetic acid, was the one who picked up a proton? You can immediately tell that it's hydroxide. So this is the conjugate acid. This is the pKa relevant for us for our comparison. I put here the pKa of water because you need to be able to identify which are the values that you're looking for. If you're attempting to compare the pKa of water, this is irrelevant. However, we need to compare the pKa of the acid, the species that acted as the acid, the one who donated this proton. It became now negatively charged carboxylate, and donated the proton to the hydroxide ion, to water, which is now the hydronium ion. So in other words, if you know what pKa's values to look for, then you will be in a good shape. Which pKa values we need, of course, our acid and our conjugate acid. We don't care about the pKa of the base. In this case, water was the base. And just to practice your arrow pushing, all of you should be very, very familiar and proficient in drawing the arrows for proton transfer reactions. Now, once we've identified both acids, the acids and the conjugate acid, then we need to know which of the two acids is weaker. In other words, which one has the higher pKa, because we know that the equilibrium is going to favor a weaker acid. In this particular case, we're comparing negative 1.7, very acidic, versus positive 4.7. So this is the weaker acid, and therefore the equilibrium is going to be favored as drawn to the left or toward the reactant. I cannot emphasize enough, if you're able to recognize the two acids in questions, the acid and the conjugate acid, then you can compare the two, and the equilibrium will lie toward the weaker acid. You always want to form weaker acids and weaker bases. If you draw the reaction in the opposite way, from right to left, then this will be the base, this will be the acid, this will be the conjugate acid, and this will be the conjugate base. So hopefully everyone can follow along. Now the question is, we know the equilibrium is going to lie towards the reactants in this case, because they're weaker acid. But the question is how much. We can say, okay, yeah, it's going to lie to here, but is it 60% and 40? Is it 51 and 49? Is it 99 and 1%? The question is how much. How can we tell? And so there's a very neat, handy, dandy pKa table which I posted on our course, and I would like all of you to refer to that. This is for acid-base reactions, and this will illustrate how we can use the pKa values to estimate very quickly, very powerful way to estimate quickly the direction of the equilibrium, but not only the direction, but the extent. To what extent? How much is it going to the right, or how much is it going to the left? And I have a couple of equations that I would like you to pay attention to. First of all, we know that the Ka is basically the equilibrium constant of an acid-base reaction, in which Hb plus is the conjugate acid and HA is the acid. The question that we are confronted is how much acid is going to be present and how much base, or how much acid and how much conjugate acid and conjugate base. We know that one equivalent of acid reacts with one equivalent of base to generate one of each. And so by knowing this Ka, we can know the ratio, the molar ratio of the products versus reactants. The molar ratio means, we have 100 moles of products versus 1 mole of reactants, and so on. There's another key equation to consider, and that is that the Ka is also expressed as the 10 to the negative delta pKa. What is the delta pKa? Delta pKa is the difference in pKa values between the acid and the conjugate acid. So those three equations are going to be fundamental for you to estimate the distribution, the ratio of product toward reactant, or the ratio of ionized, in which you have ions, the H plus, A minus, versus the non-ionized acid. So if you know the ratio of the two, then you can convert into a percentage. This table, I want you to please go ahead and download. We're going to work out the solution in terms of the math here, but very powerful table. And if you work out, you will be convinced that if you have, for example, a Ka, this is a relation of the products in percentage, the Ka, or ratio of reactants and products, and how does that relate with the difference in pKa? How many unit difference of pKa between the acid and the conjugate acid is required in order to get 99.9% ionization, 99.0, 90.9, 50? And I want to draw your attention, if there is absolutely no difference between reactants and products, that is, there's a 1-to-1 ratio or a 50-50 mixture of, for example, 50% ionized and 50% not ionized, then the difference in delta pKa is going to be 0. When you have that difference of 0, then you have half the molecules in the ionized form, in this way, in the products, and the other half in the reactants. If you're able to build this table, you don't have to go and through the math, the math exactly, but we'll still do some examples. I just want you to recognize, for example, if you have the delta pKa of minus 1 unit different, you have now 90% or close to 91% ionization. If you have 2 unit different in the negative way of minus 2, then you have 99% ionization. And if you have 3 unit difference, then you have 99.9% ionization. And in terms of the ratios, you have 1-to-1 when there's no difference, 1-to-10 ionized winning, 1-to-100 ionized winning, 1-to-1,000 ionized winning. The Ka, of course, is products over reactants, 1,000, 100, 10, and 1. And notice how now the trend goes the opposite. Now is 10-to-1, 100-to-1, and 1,000-to-1. And the Ka obviously goes in reverse, 0.1, 0.01, 0.001. The delta pKa now increases +1, +2, +3. And the percent ionization goes from 50 when there's no difference in pKa to 9% ionized, 0.99% ionized, about 1%, and then 0.09% ionization. So this table alone will get you a long way. Okay, so in Next class, we're going to look at examples on how we can use this very powerful table to predict and even estimate, ballpark estimation of the molar ratio or the percent ionized versus not ionized species when it comes to proton transfer reactions. And for now, this is it. We're gonna conclude chapter 2 next class, and as such, the problem set and the corresponding cheat sheet are going to be due. So please go ahead and start working on those. Thank you very much, and we'll see you in next class.